Okay, so hello everybody.
Hello,
So,
sir. Yeah, we
am I
can
audible
start.
now?
Yes, sir, you are audible. We can start.
Uh, I'll just go to the presentation part of it. So, is the presentation visible now?
Yes, sir, it is visible.
Okay, great. And we can start.
Yes, sir, we can start.
Okay. So, just to have a quick recap, we were discussing about lithography, where we said that we wanted to, uh, it's a definition step, and we wanted to transfer a certain pattern on the photoresist. So these are some of the tools that are used for doing lithography. Basically, you have the optics, and then you have the alignment, matlab UV source and some sort of XY stages, a combination of them. And then, for Z movement as well. And somewhere here could be the mask play where you can place. You can place your wafer, some vacuum chuck, etc., etc. Then you have, what are called as proximity printers, where there is a gap between the mask and the wafer. You have contact printers where the mask touches the wafer, and then you have a stepper, wherein you have a very high resolution mask, and it basically prints at one place, and then it steps, moves here, prints, and steps. So that is a stepper. Uh, Spin coating of the photoresist is shown in this particular slide. Essentially, you dispense a drop on the wafer and you spin it at a high speed so that the excess photoresist is splashed away. You can see the color of the photoresist here and the spinner, the photoresist spinner. So here it is important that the humidity of the chamber, it's important. Its control is important because at very low humidities, the photoresist will tend to crack up because solvents tend to escape from the photoresist. And at high humidity, the adhesion between the photoresist and the wafer is going to be poor because photoresist is a polymer and humidity is water, so there is a dislike between the two. Also, the viscosity of the photoresist depends on the temperature. So temperature control of the room is important. Otherwise, you will have different thickness of photoresists and you will have different exposure times, for example. So things have to be in control. After you have done your definition on the wafer of the film of the area where you want the film and the area where you want to remove, the next step, of course, is subtraction, where you want to etch the film that you had deposited. Now you can do a wet etch or a dry etch. Wet etch will use wet chemicals, acids, bases, for example. Dry etch will use a combination of gases in a plasma chamber. Again, all the precursors are basically going to react with the components of the film, form some volatile components, and those will be removed in case of dry etching. In case of wet etching, they will be dissolved in the solvent. You have isotropic etching, which is equidirectional, so as to say. Etching is same in all directions. You have anisotropic etching, where along certain planes, the etching rate is very slow. Along certain planes, the etching rate is very fast. So those things are possible. You can make different kind of structures, for example, notch with anisotropic etching. There is a technique of planarization, where after etching, you might have some sort of a rough edges somewhere. So you can planarize. You essentially have some sort of a plate which rotates, and you will have chemicals which are in the form of micro spheres. So those would be basically used to planarize the surface. Yeah, this is one important slide of surface micromachining and bulk micromachining. So we know that in a MEMS structure, in a MEMS device, there is one structure which has the ability to move, which means that it should not be stuck with the surface at that particular area. Now, which also means that you need to free it. You need to make you need to make room for it. So there are two different methods of doing that. One is called as surface micromachining. Here is an example. You have silicon wafer. You start with it. You either deposit or grow silicon dioxide, and you want to, let's say, create a pattern of polysilicon. So now you etch your silicon oxide here, and then you deposit polysilicon. Okay. Now, silicon dioxide is the sacrificial material. So if you again etch silicon dioxide in an etchant which does not attack polysilicon, then this layer will get removed, and you will have this structure of polysilicon which is now suspended. So it can move up and down. You can also do what is called as a bulk micromachining, where you etch the bulk itself. So here is an example. You have the substrate here, and you have a planar, you have a non-etching sort of a mask here, and you have created some sort of a hole in the mask, so that now this pattern is visible, and the silicon or the bulk is exposed. Okay. Now you can put it in an etchant which etches the silicon, right? So you will see that cavity will be dug below the cantilever region that you wanted to protect. That could be silicon dioxide, and this is now free to move. So in this process, the substrate is consumed while micromachining, while etching, and therefore it's called as bulk micromachining or bulk etching. In this case, the substrate is not consumed, and therefore you call it surface micromachining. Okay, I'll just skip with this. I talked about wafer bonding. So, let us say you want to make a sort of a pressure sensor, and you have made your device, which is like this. Now you want to have a cavity so that, you can sort of a back plate, so that this, let's say, can hold a certain gel, a certain jelly. You might want to have that. Okay? So how do you do that? Now there are various techniques of sticking two wafers together. There are certain requirements. For example, it should be very smooth, it should be very flat, no voids, the temperature expansion of the two materials should be same, etc. There are two popular methods. One is called as anodic bonding, and second is called as thermocompression bonding. Thermocompression, you essentially have a sort of a glue layer here, and glue is not the actual glue, but some other layer. And then what you do is you raise it to high temperature, apply a huge force, and it sticks. The other is called as anodic bonding, where you will have some sort of a, let's say you want to have a glass here, right? And you apply a voltage across the glass and the silicon. You keep it at high temperature. Some ions, particularly the sodium ions, they can move and they can form, or the oxygen ions, they can move, they can form a bond with silicon dioxide, and that's how it forms a bond between silicon and silicon dioxide. So I was talking about oxygen ions moving, by the way. Here is an example how you will make a micro motor. What you have done is you have added a lot of stuff here, and then you have removed. So now this, if this is the rotor, this can move, and you can control the rotation by applying voltages on the poly 1 and poly 2 electrodes. So from the top view, it looks like this. You start with the wafer, deposit one layer, etch it, deposit the oxide, make dimples in the oxide for surface micromachining, helps in faster release. You etch it, deposit the poly 1, the electrode that I talked about, etch poly 1, deposit the oxide 2. This is the sacrificial oxide. So at this point, you have a cross section which looks like this. You will etch oxide 2, you will deposit poly, again etch poly, and finally, you have this oxide that you want to remove. Okay, so when you do that, you will have a structure which is like this. So oxide removed everywhere, and this rotor is free to rotate. So this is the micromotor now. We'll not get into this again in detail. Need to go a little bit fast. Yeah, so for microfluidic devices, most popular applications are that are in the pipeline are in the bio area. The idea is to use small sample size as we had discussed in the past. Some small scale phenomena. You have seen insects walking on water, surface tension. You have seen droplets of liquid, of rain, for example, again surface tension. And you have seen, in fact, you can see this actually. If you have a micro channel, you wish to flow multiple liquids through it, then they will always go in a straight line for a reasonable length. This is because typical Reynolds number are small, and the turbulence actually doesn't happen. The turbulence happens at a much higher Reynolds number. Of course, you may want to increase the pressure so much that you want to make it turbulent, but that is also sometimes physically not possible. An example of ISTAT, which is a portable clinical analyzer. Again, lots of chemicals can move reactions inside, microfluidics inside. A lab on chip, this is one lab. You do all sorts of chemistry here. Can you do it on a chip? Same reaction chamber, same chemical, same fluidic path. Can you do it? There is a good journal on lab on chip, by the way. You may also want to access to that kind of journals. Okay. So that finishes one part of what I wanted to talk today. The second part is, what we do at Nanosnif. So as I said, that we work with two kind of MEMS devices. One is micro cantilever, second is micro heater. In this picture, this part is your cantilever. This is the substrate, and this is the hinge reel. You can see the dimensions, length, width, and thickness. And you can see that the thickness is much small as compared to the length and width. This is free to move. What can happen is this cantilever has a certain resonant frequency. Let's say it is vibrating, and some sort of a mass gets added to the cantilever. Due to this, what will happen? The resonant frequency of the cantilever will change. And therefore, this now becomes a weighing balance. Okay. However, you cannot really use it for your normal applications, weighing vegetables. But people have weighed or detected the adsorption of a single molecule onto such microcantilever structures. So it's so sensitive. The second thing that you can do is, use it as a thermometer. Let us say you have a cantilever made up of it's a bimaterial cantilever made up of two different materials. This is one, this is second, and their temperature coefficients of expansion are different. So if, let's say, you do a chemical reaction on the cantilever, the temperature will the reactions are either endothermic or exothermic. So the temperature will change. Now, since the cantilever, this material is stuck with this material, and there is a temperature change, and the temperature coefficients of expansion are different for the two materials, the cantilever has no other option but to bend. So it can bend upwards or it can bend downwards. So its bending is a indicator of a change in temperature. That is what I wanted to explain. So it becomes a good thermometer. You can detect, for example, a 0.001 or even less than that kind of temperature change. The third example is measuring change in surface stress or detecting. This is what we actually use. What we do is we coat what are called as antibodies. I'll give an example of COVID, for example. Okay, so you have the coronavirus. Suppose you coat this structure with antibodies to that coronavirus. Now we know that antibody antigen interaction is highly specific. And let us say now you have a sample in which those antigens, that is coronavirus, is present. Then the coronavirus is going to preferably stick to these antibodies. Okay. Now what happens because of that? Because of that, the surface energy here is going to change. The surface stress will change. And because of the change in surface stress, this can move upwards or it can move downwards. So gravity is not important. The change in surface stress is important. And the bending of the cantilever then becomes an indicator of the fact that the antibodies have found the coronavirus and they have stuck together. Right? So it becomes a surface stress sensor, or you can call it an antigen sensor or something like that. You may have on a cantilever, you may have a compressive stress or a tensile stress, and accordingly you will have the bending. What is important here is that this bending is going to have a certain radius of curvature. And this bending is going to have a certain deflection, okay, given by delta Z. Now, the radius of curvature is a function of the material properties and the geometry of the cantilever structure. For example, it depends on the Young's modulus, it will depend on the thickness, it will depend on the Poisson ratio. Okay, and there could be some more things that are put inside the equation. But also it depends on the surface stress. So if you can measure the radius of curvature, you will find out what is the surface stress between the antigen and the antibody. Okay. Similarly, this deflection is again a function of the material properties, let's say the Poisson ratio, and the length, for example, which is a geometrical parameter. And it is proportional to the surface stress. Okay. So if you know the deflection and you know all these properties of your device, then you can know the surface stress because of the antigen-antibody interaction. The equations for the bimetallic effect are also simple. In this equation, this is the deflection. You ignore everything that is given here. This is TCE of material 1, TCE of material 2. If these are different, if there is a change in temperature, there will be a delta Z, right? So that's how you can find out the change in temperature. Then for resonant frequency, frequency is a function of the mass. If something absorbs on the cantilever, the frequency will change. So if you are sweeping a frequency on the cantilever, and if you find that the resonant frequency has changed, it indicates that a mass has absorbed. Okay, now the cantilever has bent. How do you know that it has bent? So you need some sort of a detector for the cantilever bending itself. One way is called the optical technique, where you shine a laser on the tip of the cantilever and you collect it by a array of photosensitive diodes. So as the bending happens, different diodes will be fired, and you will know, how much it has bent and whether it is bent or not. This is the optical technique, a little bit difficult to use. At Nanosnif, we use the piezoresistive technique. So in our cantilevers, we embed a piezoresistive layer. Okay, so this is the top layer, let's say the immobilization layer for the antibodies. This is the bottom layer, let's call it the structural layer. But this layer in between is the piezoresistive layer. And the electrical contact is made with the piezoresistive layer. So, Wheatstone bridge. So this is an example of a half Wheatstone bridge. This can be the measurement cantilever. This can be the reference cantilever. So if this bends, then the piezo resistance will cause a change in resistance. And using the contacts, you can measure the change in resistance. I talked about LPCVD, if you remember. I said something about hot wire CVD. So this is a tool that I had built at IIT Bombay for my PhD. This enables low deposition of thin films such as silicon nitride, polysilicon, doped, and undoped polysilicon. But the advantage is that you can do it at a very low temperature, something like even 150 degrees Celsius, as opposed to maybe 300 in plasma CVD and about 650 in LPCVD. So it has all those, bells and whistles in the form of pumps and gauges, and mass flow controllers and cylinders, which are behind this wall, of course, mass flow controllers, etc. The point that I wanted to mention is that, let's say you have a system, you deposit a material. When you deposit a material, you should know what its material properties are. So one way of finding out the material property is to do a FTIR to see if there are silicon nitride bonds. If I have deposited silicon nitride, I should know it. I can measure the density using various other techniques. I can see if I can do a micromachining. Now, see, this is the world's first hot wire CVD silicon nitride cantilever. Okay, so you deposit the silicon nitride on a silicon wafer, you etch the silicon nitride, and then you etch the silicon in bulk, that is in the beneath. You have protected the silicon nitride here, so this remains suspended. So that's how you make a silicon nitride cantilever. Similarly, we also deposited polycrystalline silicon for the piezoresistor. So we wanted to know various material properties. For example, what is the orientation of the crystals? We found that it was 111. Then what is the grain size? What is the density? What is the resistivity? So those all questions were answered. How does it look, for example, from the AFM? What is the surface morphology? Using Raman, we found out what is the crystallinity. So our hot wire CVD film was very close to the films that we get in the LPCVD. Okay. So let's say you have deposited materials, you have investigated material properties, you want to build a structure, but before that you want to do some simulations. So the tool that I had used for simulation was Coventerware. There are other tools as well. For example, I think COMSOL is there. That's a good tool. There are more as well. Even ANSYS also does some good simulations. In simulation, let's say you want to simulate the behavior of a cantilever structure. So what you do is you can define a mass in the simulator itself. You can define a process, you can design a mass, you can generate a solid model. Then comes the important action of meshing. So you have to select an appropriate mesh. For example, we selected Manhattan parabolic. How that is selected, I'll come to that point very soon. Then you have to label various parts and then apply the boundary conditions. Now the boundary conditions, for example, I want to say that this end is the fixed end. At this end, I'm going to apply the load. This part I'm going to keep at 1 volt. This part I'm going to ground. Okay, so those could be the boundary conditions. You need to supply the material properties to the simulator, and you have to give the right units. Otherwise, it behaves very funny. You have to tune the simulator. In the sense, what we do is that you have, let's say, done some theoretical calculations that if I give a certain amount of force at the tip of the cantilever, it will deflect by this much. Then does your model actually do that? So is your model correct? And this is the place where we found out that Manhattan parabolic was a very good meshing strategy for our structure. So some investigations. The question that we were trying to answer in the slide is that if the force due to antibody antigen interaction causes a stretching in this direction, what is the change in resistance? If it is a compression in this direction, what is the change in resistance? Vis-a-vis, opposed to that, if I just bend it, then what is the change in resistance? Right. So those are some of the questions that we have answered. Other questions, if you change the material properties, if you change the top layer, the bottom layer, what happens? If you change the location of the piezoresistive layer with respect to the structural layer, it can move up and down, what happens? If you immobilize on the bottom side, what happens? Right? So those are some of the questions. So this is the design of the cantilever. This cantilever theoretically should have had a stiffness of, no, in fact, simulation wise, it had a stiffness of about 0.31 Newton per meters. We fabricated this cantilever through various steps that I mentioned, deposition, lithography, etching, etc., and final release. These are the cantilevers that we fabricated. This is a SU8 cantilever, a polymeric cantilever. This brown is the piezoresistive layer. This is the half bridge. These are the contact pads, and this is the entire device. And this is the cantilever. This part, this small part is the cantilever. This small part, for example, is the cantilever. Now, this device needs to be characterized. When I say characterization, I will like to find what is the stiffness of the device. So what do is we bend the cantilever with another cantilever whose stiffness is known. That is, spring constant is known. What happens is that these two cantilevers form a spring system in series. And if you know the total stiffness and if you know the stiffness of one cantilever, then you can find the stiffness of the cantilever that you had fabricated. So these measurements can be done in an atomic force microscope setup. We selected silicon nitride cantilever. Stiffness was given by the supplier. With the help of that, we bent our own cantilever. I will not get into this particular thing, but this is the AFM measurement. We evaluated using these graphs that the found stiffness of the sample is about 0.25 Newton per meter. So it's very close to the simulated one. So we were confident with our measurement. Then the cantilever that we had fabricated can also be put in the nose holder of the atomic force microscope, and it can be vibrated. And then you can find out what is its resonant frequency. So those measurements were done. In fact, we found out the resonant frequency to be about 40 kilohertz. Then the final, piezoresistance demonstration. So we had a very nice electrical setup to measure the resistance of the cantilever, very sensitive and all noise corrected. And we had used a probe station to deflect the cantilever. Those manipulators can be used to deflect cantilevers. So we found that, as you deflect, there is a change in the voltage. So piezoresistance was again a concept that was proved because you are actually feeding it with a constant current source. So if resistance changes, the voltage has to change. Okay. So these are the cantilevers that we fabricate these days. These are not made in SU8. These are made in silicon nitride. And the thing that you see in brown is the polycrystalline silicon. Again, the process is similar, not getting into that. What is important from the perspective of the engineer is that in making cantilevers, you need to remove the bulk. The substrate in the cantilever region has to be removed. So initially when we tried, it didn't get removed. Then we could remove a part of it. Then we could remove even more part of it. And finally, we have cantilevers which are absolutely free. These are bent in this region. Earlier, we had a bending which is like this. Very bad, something like the trunk of an elephant. Then using certain annealing techniques, we managed to straighten out the whole thing. Okay, now the applications. So we had two applications in mind. First application was to use it as a explosives detector. The idea is something like this. that explosives have a very low vapor pressure, so you cannot smell them. And the terrorists basically uh, take the advantage of these facts that they are hard to detect. Uh, the vapor pressure that you can see here is either of the order of millitorr, sorry, microtorr or nanotorr at room temperature. And therefore, we thought of making some sort of a electronic nose. The idea is like this: that let's say you have a cantilever and it is coated with a layer which has an affinity for those explosive vapors. Okay. Now, in the presence of the explosive vapors, they will bind with the coating and they will cause a bending. And if you have a piezoresistor, then you can pick up the change in resistance. So we had actually built a nice handheld device which had the cantilever inside. It had some sort of a cell, it had a pump, it had the electronics that was monitoring the resistance of the cantilever, and it had a nozzle. So when we were exposing it to explosive vapors, we saw that we could see bending, we could see some sort of a signal. So we knew that some sort of a binding and bending was happening. However, our technology faced a certain problem, that this particular thing was not highly selective, in the sense that it responded to a lot of other things. For example, to shoe polish, to various perfumes, to attar, to even I think sometimes even water vapor. Now that was a problem, because with any good sensor, the selectivity also has to be very high. Okay. So we shifted onto a different technology. The technology that we use today is based on micro heaters or micro hot plates. Again, the process of making a micro hot plate is, in fact, first I'll just describe the device. The device is here. You can see that this is half millimeters by about half millimeters, 0.5 mm. And this particular region is the membrane region. The thickness of the membrane total is less than 1 micron. Okay. At the bottom side, you have silicon dioxide. At the top side, you have silicon nitride. And in between, you have these two zigzags. One is the heater part, and the second is the thermometer part. So if you apply a voltage to the heater part, a current will flow, typically a few milliamps, and that is going to heat up the microheater. From room temperature to 500 degrees Celsius, it takes about 3 to 4 milliseconds, and it cools down equally fast. In about 5 to 6 milliseconds, it will come back to room temperature. The other platinum coil, which is used as a temperature sensor, so that is, to that you don't apply a voltage. You force a small constant current through it, about half milliamperes or maybe 1 milliampere. And as the temperature of the membrane has increased because of the heating coil, then this temperature sensor, its resistance is going to change. Okay, because of the TCR of the platinum material. And if you are monitoring the resistance, you can monitor or measure the temperature. So that is the basic technology. The advantage is that you can go from room temperature to high temperature, that is about 500 degrees Celsius, very fast in a few milliseconds. And this is what we exploit in microheaters. So I'll just show a small video of a microheater. Please remember that in this video, the microheater is being driven by a low frequency sine wave, so that we could actually capture the heating and cooling of the microheater. So I'll play it once again. it's not playing.
Sir,
Yeah.
sir, I have one question. So,
Yeah.
what is the material used here to making this heat by giving the low frequency sine wave?
The material is platinum.
Okay.
So for some reason, I think it's not playing. Anyway, I'll go to the next slide. Or maybe come back and try to play. Yeah. So any questions on this? Okay. Then I'll go ahead.
Hello.
Yeah.
Hello, Kale sir.
Ha.
Sir, this is Sanket from Nagpur. Sir, I just want to ask one question that which type of material should we use to detect various biosensors or various VOCs?
So, I'll keep this question to the last part of it.
Okay, okay, sir. Okay, sir.
Okay. Yeah. Thank you.
Okay, sir.
Any other question on micro heater? Okay. So what we do in our strategy of detecting explosive is that we transfer the small quantities of explosive on this micro hot plate, micro heater through some technique, and then we rapidly heat it. So if it is an explosive, there is a micro explosion called as deflagration, and we get a temperature signal which is like this. If it is not an explosive, we get something that is very flat. I mean, it's not so easy. There are a lot of things that go in between. And for that, we have got some very intelligent algorithms which are going to analyze the data. This is the Nanosniffer instrument that we have developed, and we have actually started marketing it also, showing demonstrations. So it detects all types of explosives up to even less than 10 nanograms. We require hardly 8 to 10 seconds to detect. It's a sort of a handheld, light, battery operated. Works at high temperatures also. Somebody said that you are from Nagpur, so it will work at Nagpur, 48 degrees, 49 degrees Celsius also. So I'll just show a demo of that. So you go around that. You insert a blank swab, and then you run. The blank doesn't have an explosive. So a message will come here in green color saying no traces detected. That's the message. You remove the swab, put another swab which has 10 nanograms of RDX. You run it. A message will come here in red color saying traces detected, and you will also hear a beep. You heard the beep, right? So this is the message in red as well. I'm playing it once again. Do you hear the beep? So any participant, did you hear the beep?
No, sir.
Yes, sir.
Okay, good.
Yes, sir.
So we'll go to the next slide now. Any questions on this? Or maybe we can keep it to the end. We'll have about 15-20 minutes of Q&A. Okay. Now, at Nanosnif, since cantilevers were not found useful for explosives detectors, the other application for cantilevers was to detect antigens. And so we said that, okay, let us try to pick up a certain problem for detecting certain proteins with the help of microcantilevers. And the identified problem was detecting heart attack, potentially detecting a heart attack. We all know that today heart disease is a major problem in India. It's also affecting the young. But the issue in detecting whether a heart attack, whether a person is undergoing a heart attack, that's very difficult for the doctors. There are various reasons for that. First is, a chest pain could be because of gas. A pain in the shoulder could be a heart attack indicator. Heart attacks do not show up in 50% of the ECG cases. They are called as non-STEMI attacks. The thing that doctors most trust on is the presence of cardiac markers, specific cardiac markers in the blood samples, such as troponin. The problem here is that if you want to detect the cardiac marker in the blood sample, you need to send it to a lab, a pathology lab, and it easily takes about 4 to 6 hours for the tests, for the transport and the test to be done. And during this time, the damage to the heart muscle has already occurred. And in case of heart attacks, it's said that the first 1 to 2 hours is the golden hour, where much of the heart muscle can be saved. So what is needed is some sort of a point of care instrument that can quickly give a yes or no decision for the doctor. Okay. So we thought to explore in that direction. These are some of the cardiac markers: myoglobin, troponin, CKMB, fatty acid binding protein, lot of things. Troponin is something that is very specific, but it peaks much later. So you need a very high sensitivity instrument to actually detect troponin in low quantities. The idea is simple: antigen-antibody interaction, as I had indicated earlier. The antibody coated on the cantilevers, looking for the troponin proteins. If they are present, then binding and binding. The key thing here is that this is the structure of the antibody, Y-shaped structure. This part is common for all antibodies. Only this part changes. Okay, so this is a lock and key mechanism. This is your antigen and this is your antibody. So for each type of antigen, you will have its antibody. You do what is called as chemical surface modification or chemical functionalization, so that these antibodies can be stuck on the surface of a cantilever. The method is, I would say, it's normally secret in most of the companies, but a lot of general methods are available in the literature. You essentially coat some sort of aminosilane, then a linker molecule, then the antibody, and so it's ready for the antigen attachment. And of course, this is the cantilever structure. So before you do cantilever-based protein detection measurements, you need to know whether your immobilization of antibodies on the surface of the cantilever has been successful or not. Here is an example which depicts that. So for that, what you do is you use fluorescence antigens. So you have your surface, any surface. For example, this is a silicon wafer surface, but it's a big substrate. This is also a big substrate. So on that, you do all the things that I talked about, functionalization, and then eventually you have the primary antibody, then your fluorescence antibody, etc. So you can see that fluorescence is observed under microscope. So you can be confident that the process is correct. And then you can repeat that on the cantilevers. This is the example. A few of my colleagues, maybe about 8-10 years back, had worked with this and demonstrated optical detection. So as I had said, you can put the cantilevers in the nose of the AFM, functionalized, and then you have liquid cell, and then you have all these things flowing in and out. And here, for example, he demonstrated that there is a deflection because of attachment. Okay. But we wanted, electrical detection. So that was something more, or in fact, a lot more was required to be done for that. So how do we do that? So the method is like this, that we use a setup which is shown here. This setup has the electronics which is required to monitor the resistance of the cantilever. The monitoring is done practically about 4 to 8 times a second of all the cantilevers. This we know is the cantilever die. This cantilever die is attached on a PCB. Then you do what is called as wire bonding from the die to the PCB. On this side of the PCB, you have the connectors. Okay, so this forms the electrical device. Then you have the mechanical part, because you are going to flow liquids. So you need to kind of cover the cantilever region so that the liquids do not seep away to the contact pad area. So the sealing should be proper. And then you have, this as the inlet and this as the outlet. You can concentrate a bit on this T. So this is that T. This is a syringe pump. It has stepper motors, and you can push in liquid from one syringe through this T into the liquid cell so that it can interact with the cantilevers. What is typically done is, first things are what is called as equilibrated. So you flow the liquid through the cantilever for some time, the resistance stabilizes, and then you push in the antigen solution, the thing that you are interested in. So you can see this path now, it is very clear. And what you can also see is that this connector region is connected with the electronics, which is monitoring the resistance of the cantilever. Yeah, so you flow PBS, over a period of time it stabilizes, then you push in the antigen. When you push in the antigen, it flows from here to here. It takes some time. And after some time, you will see that the cantilever has deflected. It indicates by a change in its resistance. So this is what we were looking at. And since then, we have tried with not only IgG, anti-HIgG pairs, but with myoglobin, with fatty acid binding protein, with troponin, a lot of all these biochemicals, and we have been successful in doing these experiments. Any questions till this point? Okay. Now, here are a few slides which depict, how you can use the devices that we have developed and the instrumentation that we have developed for doing research at your institutes. So one of the instruments that we have developed It's called as OmniCan. And with this, you can experiment with micro cantilevers. We have discussed about how to fabricate cantilevers, so we'll not get into that. Now let us see how to monitor cantilevers. So the example is something like this. That in gas chromatography kind of analysis, they do what is called as analysis of the head space. When I say head space, it's nothing but a bottle in which I have filled analyte up to this level. This area looks empty, but it's filled with some of the vapors of the analyte. The best way is to take these vapors by some mechanism to your analyzer and try to analyze what is there inside, right? So that's your headspace analysis. We try to do that with microcantilevers. This is the instrument. Okay. This is the place where you can fit your vial, which will contain the chemical that you are interested to analyze. This pipe that you see is the inlet pipe, and this is the outlet pipe. This comes from inside into this reaction chamber. So this is the reaction chamber. And this is the electrical connection for the reaction chamber. We call this as the flow cell, and this is the connector other part. The cantilever is present inside this. Okay. So when you fit this here, the gases that are coming from the flow path are going to interact with the microcantilever. This is how the PCB looks like from another view. The flow cell is fitted here, and the connector is here, and this is the die. Okay. These are some of the specifications. Basically, it's trying to say that it's a plug and play kind of instrument, and it's highly sensitive. So, this is an example of what is achievable with OmniCan setup. First thing is, if you change the flow rate, you will see a deflection. So it's a flow rate sensor. If you put in acetone, you will see a deflection because of the coating and cantilever. If you put off acetone, you will see a deflection. So this is very faithful. This is the second thing. Third thing is that you have seen a drift. This drift is in the electronics. We have corrected this. So this can actually be something like this. Okay, straight line now, parallel to the x-axis. The drift has been removed. Why I like to show this graph is, this is the first time we did this experiment about 9 years back, and we got everything right, this result itself, the very first time in such a complicated setup. Now, you can do a lot of experiment with this setup. For example, you can change the coating on the cantilever. You can change the volatile compound in the flow, in the liquid cell, or in that headspace vial. You can change the temperature of the heater which you are using to create vapors in the headspace. You can change the temperature of the reaction chamber. Reaction chamber is called a sniff cell. You can change the temperature there. So you can see how the reactions happen at higher temperatures. You can also change the flow rate of the carrier gas. Now, when I say carrier gas, what I mean basically is that vapors do not come automatically to the chamber. They are brought to the chamber with the help of carrier gas, whose flow rate is controlled. So there is a mass flow controller to do that job. The electronics is highly sensitive in the sense that you can detect a change of 1 ohm in about 47 kilo ohms with about 100 nanoamperes of current. This is to avoid self-heating in the cantilevers due to a flow of current. You can see that 100 nanometers is a very, very small amount of current. This is another instrument. This is again very nowadays popular with a lot of engineering colleges, called as sensimer. I think STPI, your Bole sir, your sister, organization also.
SPIT.
Yeah, yeah,
Yeah,
SPI.
SPIT is having.
Yeah, yeah. So Professor Rathod there had actually procured this from us.
Yeah, yeah.
This and the MEMS micro heaters.
Okay.
So this is used actually to do experiments on the micro heaters. I'll give an example. Uh, at this part, you can fit the the micro heater PCB. So the connections you make with the connectors and the micro heaters, and you can fit it here. What this instrument does now is it applies excitation to the micro heater and it measures the temperature of the thermometer. It is the other platinum coil. You can apply different kind of waveforms. You can do a sine wave, you can do a triangular wave, a square wave, a trapezoidal wave, whatever. Okay, and you can see how the temperature changes. Right, you can do the timing control as well. You can find out the rise time and the fall time. This is a typical curve. If you apply a square wave, then about in 5 to 6 seconds, it will reach to its 90% max. It takes about maybe 10-12 seconds to fall down for this example. Temperature is about, about 600 plus degrees it has already reached. Okay. So these are some of the experiments, finding rise time, fall time, and a lot of other stuff. What could be interesting for you people is something like this. That if you put a grain of salt on the micro heater membrane, then the thermal mass of the micro heater increases. So it will take more time to heat up, right? So the rise time is going to be more. Now you can have a calibration situation. You put different 1, 2, 3, 4, 5 grains of salt, and you kind of find how much is the change in rise time. So that could be some very interesting experiment for PG students, or maybe even some higher level BTech students at your labs. For sensors, instrumentation, MEMS, etc. These are good kits to play with. Okay, I'm coming to kind of the end of my talk. The last 15-20 minutes we can have some sort of question answers. I like to have that. So what we are also doing now is we are making some new devices. We have made, for example, cantilevers with 8 of the dies. Okay. We have made, sorry, not 8 dies. We have made cantilever dies in which you have 8 cantilevers per die, and you can then go for detecting multiple gases if you want, or multiple volatile organic compounds if you want to play with. If you want to play with different coatings, you can do with a 8 cantilever die. This is one. Second, if you have a look at this picture, what do you see here is a micro hot plate that I had anyway initially showed. But on the micro hot plate, we have also put what is called as interdigitated electrodes. So this one set of fingers is on the left hand side, one set of fingers is connected to the electrode on the right hand side. Okay. Now, where is this useful? This was actually developed for the Space Science Institute at Trivandrum. That's IISST or something like that. They wanted to make a ammonia gas sensor. For that, their idea was, so the overall idea is something like this, that metal oxide films are highly sensitive to certain gases. And in fact, I would say many of the gases. However, they respond nicely at high temperatures, elevated temperatures. It's different for different gases and different coatings as well. So the idea was that this microheater's job will be to elevate the temperature, and the job of the IDs will be to monitor the conductivity of the metal oxide film. So if the gas molecules are there, they will come, they will interact with the metal oxide film, cause either a reduction or oxidation reaction, due to which the conductivity of the film is going to change. And that is being monitored by the interdigitated electrodes. That was it. So they have done quite a good amount of work now using these devices. So this is an interesting research application. So I guess I'm kind of towards the end of my talk. I have discussed about the devices, this part of the talk, that is, I've discussed about the cantilevers, about microheaters, about instruments which you can use to monitor these devices. Also discussed about explosives detectors and cardiac marker detectors, etc. So, yeah, this is my last slide. This has nothing to do with MEMS. It talks about something which is called as the Pasteur's quadrant. This is from a book by Donald Stokes, Pasteur's quadrant, and the title is A Basic Science and Technological Innovation, published in '97. The idea is that, you know, the research path and the product development path can be such, looking at Pasteur's work, where applied goals are not inherently opposed with scientific creativity and rigor. The idea here is that if, for example, when you do a certain product development, you need to do, you know, hundreds of thousands of tests. The idea is they can still be interesting. That's the idea. What the Pasteur's quadrant does is, you know, it maps knowledge creation with knowledge utilization. And it takes, of course, there are 4 rectangles in the quadrant. It first talks about, you know, a situation which he calls as teaching oriented research. The example is the great philosopher Socrates. Now, in his case, knowledge creation is less and knowledge utilization is also less. For Socrates' case, okay, teaching oriented research. The other example is pure applied research. The example is Edison, who of course created that bulb. In his case, the knowledge utilization is high, but the knowledge creation is low. The example is, you know, Edison required something like 40,000 experiments to determine the material for the electric bulb. So utilization was there, but, you know, creation was not there, because that material could be found out, you know, in maybe half a dozen well-planned experiments. That is what his competitor Tesla used to say. Okay. The third case is pure basic research. Pure. Example is Niels Bohr, where the knowledge creation is very, very high. You know, structure of the hydrogen atom, quantum mechanics. So the knowledge creation is very high, but utilization, at least in his times, now of course there is some work, but at least in his times, there was hardly any immediate utilization of the knowledge that he had created. The best example is, the fourth example is from Louis Pasteur. So Louis Pasteur is use-inspired basic research, where knowledge creation and utilization is very, very high. So what Pasteur did was that Pasteur was a chemist basically, and he found out that milk that goes bad, it has a certain microscopic reason. And the microscopic reason that he determined with the help of a microscope were bacteria. They were moving all around, swimming and playing all around, dividing also. So he said that if he gives a heat treatment the bacteria being organic matter are going to die, and the milk will stay. I mean, it will stay good. Now, his solution was something that is scalable as well. So everybody in the world now boils the milk. In fact, during from his time itself, they would have started boiling them, right, to kill off the microbes. So that is pure applied research. Other example is, of course, the rabies thing. It's a very famous story that Edison used to play with vaccines, and he had actually prepared a sort of a vaccine for rabid dogs, and there was a case of a boy who was bit by a rabid dog, and the dog died because of rabies, and Pasteur managed to persuade the parents of the boy that he could be injected with that particular vaccine, and the boy survived. So vaccination today, again, as you can see, although I won't say that Pasteur was the person who discovered vaccination or immunization technique, but he has a major role to play. At least his idea of use-inspired basic research is also kind of adopted in the vaccines example. So let us choose a fundamentally new or novel phenomenon. Let us understand the basic science underlying it, and then translate that knowledge into some sort of an application. So that's all I think from my side, and I'll be happy to answer any questions.
Any questions from the audience, from the participants?
Hello.
Yes, Professor Sanket, go ahead.
Yes, sir. Sir, very good afternoon, Nitin, sir. Sir,
Yeah.
I just ask you one question regarding which type of material should be coated on that micro cantilever for detection of various VOCs, that is volatile organic compound, to detect the cancer, or more specifically, detect the lung cancer.
So it's a very hard question. Actually, there is a good amount of literature that would have been done, but
Okay, sir.
cancer is something that MEMS people should not try to touch. Cancer and tuberculosis.
Okay, sir.
Okay, there are just too many other much better and much more reliable things that doctors will trust than
Okay.
cantilevers.
Okay,
MEMS.
sir.
Have I answered your question?
Okay,
Because
okay.
a lot of things have come up. There are a lot of papers with cantilevers and cancer, etc. But looking at the applications point of view, looking at the user point of view,
Okay,
for
sir.
TB and cancers, cantilevers should be kept away.
Okay. Sir, as you just show us that explosive sensor.
Yeah,
Hello. Oh,
yeah.
sir, on that basis, can we create the sensor for detection of cancer?
No, see, the reason why it works to detect explosives is that explosives deflagrate at high temperature.
Okay.
Okay, so they explode, and that is why there is a change in temperature.
Okay.
Okay, which our sensor picks up.
Okay, sir.
Cancer cell is not going to have that.
Okay, okay, sir. Thank you, sir. Thank you.
Yeah, welcome.
So can we use this
Yes.
MEMS as far as detection of this COVID-19?
Okay, so in principle, yes, it is possible. Yeah. So in principle, it is possible, as I said.
So in what way we can use these MEMS as a this sensor?
So as I said that you could have the antibodies to the coronavirus coated on the cantilevers,
Yes,
and
yes.
then you can have samples that are introduced in a proper liquid cell after doing proper engineering, in the vicinity of the cantilevers, and then binding, bending, and electronic monitoring will give you the detection.
Thank you, sir.
Okay.
Sir, good afternoon, sir.
Yeah.
Yeah, this is Dr. Jagdish Chandra calling from Vizag, sir, Andhra Pradesh.
Yeah. Yeah.
Sir, nowadays everything, whatever internal organs completely the transportation medium is blood, sir. As far as my knowledge is concerned, so the blood is
Okay.
passing through the all organs, sir. So nowadays,
Okay.
if you want to find out the early detection of the heart attacks, people are going through the either ECG or else echo. Otherwise, they have to go for angio. Angio is almost all a minor operation, sir. So
No.
I gone through some literature that troponin N enzyme is available in blood cells. So this troponin N enzyme, if you detect if the percentage of that particular enzyme is keep on reducing, by that time there may be possibility to destroy the walls of the heart. They damage this reduction of that particular enzyme damages the walls of the heart.
Okay.
So is it possible to early detection of this particular enzyme, sir, through our MEMS sensors? This is my first question.
It is possible. Yeah, it is possible.
It is possible. So
It is possible,
then
yeah.
the antibody, we have to find out the effective antibody, right?
Yeah.
And
Yeah.
also how our sensors are more effective than the already traditional sensors which are available. See, for blood glucose detection, we have filters we are using. And whatever the for 5 rupees, by purchasing of 5 rupees, we can 5 or 10 rupees from imported from America or some other advanced countries. People are measuring the glucose or fructose percentage on our blood cells.
Yeah.
So how these MEMS sensors will differ, because those are very, very low cost. So if you want to fabricate a sensor for this particular application, how much money we have to spend, how it will differ from that?
Okay, so it's a big question. So first of all, blood, for measuring sugar in blood.
Yes, sir.
Sugar is present in a fairly large amount in the blood.
Yes, sir.
So you don't need a micro sensor for that. Okay. When you have some quantity which is available in nanogram per ml kind of concentrations, only then you need a micro sensor, a MEMS micro sensor. So troponin is an example. Okay. So the application should be clear.
The sensitivity is more for MEMS based sensors.
Yeah,
sensitivity
it's
is
going to be very
in that part we can develop our own sensors, our native sensors, without importing the sensors from. But the importation cost is very low. So nowadays the MEMS is playing major role for sensors and activation applications. But these particular biosensors, maybe it is more. It may give more result, and I'm trying to do some research on that, sir, because I worked completely on clean room environment in South Korea also for MOSFET devices.
Okay.
And will you try, because I'm very new to MEMS, sir, but theoretically I have some knowledge. Practically I don't have any knowledge. So I would like to expose to some software tool to design any micro sensors or micro actuators.
Yeah, so you can contact COMSOL. They will give you a 14-day license.
Okay. In this FDP, do we have any practical session in the afternoon, sir? I'm asking the organizing committee, not you, sir. Sorry, I'm asking that organizing committee, sir.
Practical sessions we don't have. Practical sessions we don't have, but we have one orientation session on use of different facilities which nano fabrication laboratory is having at IIT Bombay. So in the last course which I have conducted, we had the visit to IIT Bombay nano fabrication and CEN laboratory, where the participants have visited the laboratory and seen the different fabrication processes and facility available. Okay. But because of this pandemic, we could not like visit the laboratory, so that's the problem. So
no, sir. This ACP FDP in the month of May, they have been conducted by using Python. They conducted online classes. Like that, for COMSOL also, is there any plan to conduct such type of 1 or 2 days classes to introduce to us?
No, that is not planned, but we have one session wherein we can visit, like we can see the different fabrication facility which are available at IIT Bombay, and how to use that, how the user program, INU program is that it is at the end of the project.
I know, sir. I don't want the
Yeah, yeah.
fabrication facilities. I want the simulators,
No, no,
right?
simulation we have not here included here in our entity.
Okay, sir. Okay. Thank you, sir. Thank you, sir. Thank you. Thank you, sir. The speakers are
Okay, welcome.
sir.
Yeah, welcome.
Thank you for your nice interaction with you, sir. Thank you so much. Maybe I will search for some more literature to identify the antibodies for this particular
Sure.
detection of the
Sure.
detection of the-
For anything with MEMS devices, you can of course write to us. No problem.
Yeah, can you share this PPT with us, sir? In that PPT, maybe we get your.
Yeah. So something at the end I'll share with Professor Bole.
Yeah, please, sir. Please, sir. Thank you. Thank you, sir.
Yeah. Any other questions?
Hello, sir. This is Shruti from KIT University. So I just want to ask that is there any application of MEMS in neuromorphic computing area?
I don't see a direct application.
Okay.
I don't see a direct application.
Okay. So can we even think of something in that field exactly in neuromorphic computing applications?
No, actually, we do not use, or we do not think of MEMS in Nanosnif in our company as some sort of a computing device. We look at it more as either a sensor or as an actuator device. In fact, more as a sensor device.
Okay.
So maybe our thinking in that direction really is not there.
Okay, sir. Thank you, sir.
Okay. Okay, any other questions? ठीक है, so Professor Kiran, I guess there are no questions.
No questions from
can wind up then.
Yeah, so thank you very much, sir, for your informative session. So it's a marathon session, 2 sessions consecutive you have taken, and you have covered a lot of things related to the MEMS fabrication processes, and also the device development for various application. You have given a good introduction to various devices and instrumentation which are developed at the Nanosnif, and hope everybody has one benefit of that. And so thank you once again, sir.
Yeah, okay, chalo.
Yeah.
Bye bye everybody, and good luck to everybody.
Yeah. Thank you, sir. Thank you very much.
Thank you, sir, for the session.
Yeah.
Thank you, sir.
Participants, next session will be by Dr. Tanveer from TUEE Switzerland. So it will be on femtosecond laser-based micromachining, and do present 10 minutes before scheduled time. So the lecture is scheduled at 2 p.m. So you can log in at 1:50 p.m. Thank you very much. Have a lunch.